Dear students, so welcome to the first lecture of microcontrollers. My name is Abhishek Nag and I will be teaching microcontrollers this semester. Um, so I'm taking this class and you are a fresh set of students for me. So all of you are attending my class for the first time, and I'm also seeing you or teaching you for the first time. Uh, Unfortunately, I cannot be in front of you all this semester because of the current pandemic situation. But but I will try my best to deliver my lectures through these video recordings, and we will interact with each other in weekly live sessions. The details of those will be given to you later, and yeah, so that's it. That's how we would be proceeding this semester. You are all welcome to contact me through my email, which is shown here. And if you want, you can also add me on WeChat. So I will share my WeChat account details with you later. Uh, but um, but right now, let's proceed with the module. So here is a brief introduction about myself. So again, since this is the first time that you are attending a lecture of me, attending a module taught by me, I thought it would be nice to introduce myself. So my name is Avishek Nag, as you saw. My students call me Nag. They also call me Avishek. So whichever way you want to call me, my first name is Avishek, last name is Nag, and I'm an assistant professor in UCT School of Electrical and Electronic Engineering, and I teach you all every autumn semester um, under the Beijing Dublin International College scheme. I had a PhD from UC Davis in USA. Then I moved to Ireland as a postdoc in Trinity College Dublin, and then from 2017 I have been a part of UCD and BDIC. I have more than 11 years of research experience, 3 years of teaching experience. My research area is IoT, 5G, optical networks, machine learning for telecom networks, blockchain, etc. You can find more about myself in my LinkedIn profile and my personal website given here. And if you are interested to do any short projects with me on any of these research topics shown here, then feel free to contact me and I will be happy to guide you. Okay, so right now I'll be teaching microcontrollers, and let's proceed with that. So the first thing is the assessment strategy that I'm going to take. And this year things have changed a little bit, as I mentioned. We are doing remote online video lectures, and the assessment strategy also has been changed a little bit. So there will be 4 labs, and 20% of your final grade will be from those labs. How we will conduct these labs this year, the more details will be given to you later. At the time of recording this lecture, we don't have the final details of how these labs will be conducted. As soon as we find out strategy, we will let you know through Brightspace or through emails, or through your class monitors, whichever way. And the remaining 80% will be continuous assessments. Again, this is a change this year than the previous years. Earlier, we used to have a midterm exam, a final exam, but this time I will have continuous assessments. So there will be multiple programming assignments or mini projects, and then there will be some quizzes from time to time. And the grade scale that I'll be following is the this one, which is highlighted in red. So basically this is a linear numeric scale where the pass mark is 40%, and to get an A plus, let's say, you have to score 95 or more out of 100. So that's the grade scale for you. And in terms of books, so there are these two books which are very good, and I usually follow the first one, the one by Muhammad Ali Mazidi. Okay, so this is a very nice book. You can find it online. They have some PDF copies available. You can find it in your library, or you can buy the book also. It's a good book to have. And I will strongly encourage you to get a copy of this book, either a soft copy or a hard copy, because this semester the lectures are all remote, video based. I would suggest you to get the book, because there might be some gaps in my teaching, because I'm not physically present in front of you and cannot address all your doubts personally. So I think the book can help you. So you get hold of the book, and I will try my best from my side to be as clear as possible when I'm explaining the concepts. And then you can read them also from the book. You can also read from my slides. I will post them on Brightspace. So, having said that, next topic is the plagiarism. So, this is again something which uh, is is a serious offense as per as UCD and PGIC policies, and I would expect and request both that you don't engage in any form of plagiarism. The consequences are not very comfortable, are not very um, welcome. So please stay away from any form of plagiarism uh, while you are writing your lab reports, or writing your project reports or anything. So now, getting into the actual concepts of microcontrollers and and then micro processors. So this module is all about microcontrollers. This module is not about microprocessor, but to introduce this module, I think we should talk about the microprocessor first and find out the differences between a microprocessor and a microcontroller. So a microprocessor is basically a processing unit, okay, a CPU, a central processing unit. All computers have a CPU, and then you attach some external blocks to it. So you attach a RAM, a ROM, a IO port, a serial port, a timer, etc. Through the buses, through the data bus and the address bus, and this is a general purpose microprocessor. So this can have different capabilities, okay, depending on how much memory and how much processing power it has. And then you interface with the other necessary blocks to make it a foolproof computer, okay. uh, Whereas a microcontroller is essentially a self sufficient unit. So all the blocks that you saw in the previous slide, I mean the external blocks, they are all embedded within the microcontroller chip. So apart from the CPU, you also have the RAM, ROM, and all the ports, timers, etc. They come as a complete package. Okay, so the main difference is this: the microprocessor is the processor itself, the standalone processor, and then you interface it with other devices to complete the design of a computer. A microcontroller is a mini computer in itself, and it's a self-sufficient unit with all the blocks necessary for the computation embedded inside the same chip. Okay, so microcontrollers typically contain a simplified CPU, which is the microprocessor, and then it contains, in addition, a fixed amount of RAM, ROM, IO ports, timers, and serial communication blocks. These are all embedded together on a single chip. And then, if you need additional memory, additional ROM, additional RAM, you can interface them externally with the microcontroller. But generally speaking, it comes with all the blocks necessary for doing a complete computation task. Okay, and and the advantage of a microcontroller is that the since the components are all self-contained, um, and you can have you can buy a chip of a microcontroller and you get all the functionalities self-contained. So essentially, you end up spending less on the application. Okay, so therefore, uh, generally speaking, it is cheap. Okay, so moving on, what are the applications of a microcontroller? So there are many actually. Whatever you see, whatever electronic gadget you see around has some form of microcontrollers embedded in them. So your TV remote controls, your washing machine, freeze, these are all having some microcontrollers embedded in them to perform some digital task. The elevators in your university, in the offices, the automatic doors, the photocopiers, uh, again, they have microcontrollers in them. The industrial systems, like the safety systems in the industry, the automated factories, they all have microcontrollers. In the car electronics, in traffic lighting, signaling, uh, collision avoidance, etc., you have microcontrollers. So most of these electronic devices or IoT devices. So you are studying, um, some of you are studying Internet of Things engineering. Uh, so in IoT, all these IoT devices which are doing some tasks based on some digital input signals, they all have a microcontroller that is helping them to perform these tasks. Okay, so now we will review some basic materials from digital electronics to build up the fundamentals. So you need some background knowledge to study a microcontroller, and I assume that you have had a course on digital electronics where you studied this, but we will review these concepts on a very high level before we proceed into the actual microcontroller fundamentals. So let's see. The first thing is the bit or the binary digit, which is a single unit of the binary number, and it can take two values, 0 or 1, and usually they are represented in hardware as voltages, where a high voltage represent a 1 and a low voltage represent a 0. A nibble is a group of 4 bits. So for example, 0010, this is a group of 4 bits and this is called nibble. And a byte is a group of 8 bits or 2 nibbles. And a word is traditionally referred to a group of 16 bits, but it can mean any size. It can be a 32-bit word as well. It can be a 64-bit word as well. So when we are having binary digits or bits, we are actually working with the base 2. Okay, so the general math that we do are in the decimal system. So when we are working with multiple bases, binary and decimal, we should mention the base with the lowercase subscript. So the number 10 base 2 represent a decimal number, um, which is represented in binary as sorry, the number 10 base 2 is actually a binary number, and it represents the decimal number 2. So 2 base 10 is equivalent to 10 base 2. So we use that subscript, lowercase subscript, to represent the base. However, often this sign B at the end of the number is also used to indicate that it is binary. So 10B or 10B is equivalent to 10 to the base 2. Similarly, hexadecimal values can also be denoted using either the subscript 16 to represent that it is a hexadecimal number system, or using an H at the end. So 1B is a hexadecimal number, and you put an H to represent that, or you can put a 16 in the subscript. Traditionally, the SI prefixes, when referring to a collection of bytes, have always indicated multiples of 2 to the power 10 bytes. So for example, 1 kilobyte is actually 1024 bytes, but this kilo doesn't mean 1000 as we mean in SI system. So this kilo is basically 2 to the power 10. Okay, and sometimes 1k or 1kb is also used to indicate this. So this, there is a confusion here. So in SI system we have 1 kilo, which means 1000, but in binary we have 1024. So there can be some confusion, and therefore to remove that confusion, a new set of prefixes has been created just for measuring the data in multiples of powers of 2. So we call it kibibyte in the new system. So basically 1 kibibyte is actually 1024 bytes. And just as in case of the decimal system, we have for different powers of 10, we have kilo, mega, giga, tera, peta. Similarly, in binary also, depending on different powers of 2, we can have kibibyte, maybe byte, gibibyte, tbbyte, and pbbyte. So then comes the concepts of LSB and MSB. So in a given binary string, if you start looking from your right to left, you get the LSBs, and from left to right, you get the MSBs. So in this case, the MSB is 1 and the LSB is 0. Okay. You can also refer to a number of LSBs. So the 4 LSBs are in this case 1001. The 4 MSBs are 0, 1, 0, 0, etc. So again, these things are known to you, but I'm just revising for the sake of recalling. So let's say binary to decimal conversions. So you can convert the following numbers from binary to decimal by multiplying the numbers with the corresponding powers of 2. So if the number is in the 0th position, let's say you multiply it with 2 to the power 0. In the first position you multiply it with 2 to the power 1, and so on, and then you add them together like this to get the corresponding decimal value. Similarly, you can have fractional values as well in binary, so denoted by a dot here. So whatever follows after this dot on the right hand side is the fractional part, and you if this is your 0th position, then this is your -1th position. So you can multiply this number with 2 to the power -1, then the next to the right by 2 to the power -2, and so on, and you can get the corresponding fractional number in decimals. So let's do a quick exercise. Let's convert this number 1010.101, which is in binary, to decimal. So if you follow the same rule as discussed, you will get this number in decimal, which is 10.625. You can also convert from decimal to binary. Okay, so the trick here is to keep dividing the decimal number by 2 until you have 0 remainder. Okay, so let's say you have 156.25. You want to convert this number to binary. So let's take the integer part first, 156. You keep dividing it by 2. The first division by 2 gives you a quotient of 78, and the remainder is 0. You again divide it by 2, you get 39 and 0. Again divide by 2, you get 19 and 1, then 9 and 1, then again 4 and 1, then you divide by 2, you get 2 and 0, and then you divide again by 2, you get 1 and 0, and the next division will give you 0 as a quotient. So here you will stop. Okay, so the stopping criteria is when your quotient is 0, where after you keep on dividing repeatedly by 2, and then you can read from this direction. This will be your MSB, and then this will be your LSB. Okay, so the number will be then 1 0 0 1 1 1 0 0. Okay, so that is your 156 represented in binary. And then what about the fractional part? For the fractional part, you do just the opposite. You keep on multiplying until you get a 0 in the integer part. So if you multiply 0.25 with 2, you get 0.5. You then again multiply by 2, you get 1, and then 0, and then that is your stopping criteria. Okay, so 0.25 is 0.0100. Okay, so you are stopping. Basically you could have stopped here as soon as you get a 0 where by multiplying by 2. Okay, sorry, your fractional part has to be 0. Okay, so whenever your fractional part is 0, you stop right there. So you could have stopped right here, but then just to check if there is anything else after that, just to be 100% sure, you multiply again by 2, and you see that you keep getting zeros here. So that is how you calculate the binary equivalent of a decimal number. And let's take this example. So 156.1. In this case, the fractional part, if you keep multiplying by 2, it never stops. Okay, so so basically the fractional part never becomes 0. When you multiply it with 2, it becomes 0.2. When you multiply by 2 again, 0.4, 0.8, then again it becomes 0.6, and so on. So the fractional part repeats, and so are these number. Okay, so basically what you can do is, when you have this 0.1 in decimal, you can see that there is a repeating pattern. Okay, 0.00011, and then it again repeats this part. Okay, basically this is the repeating pattern. 0.0 and then 0011 is the repeating pattern. So you can write this as this. So this is the concept of recurring decimal. Okay, in decimal representation also, let's say if you have 1 over 3, okay, then this is like basically 0.3333, it repeats. Okay, so you can write this as 0.3 with a dot on the top to signify that this digit is recurring. Here also, since this 0011 part is repeating, you can write it as 0.0 and then 0011 have 4 dots on top. So this is the equivalent binary representation, which is a recurring fraction. Okay, so you can do a quick exercise. We can convert this number 250.8 into binary, and if we do so, we will find that there is, so this is the integer part, but for the decimal part you can see there is a repeating part. Okay, 1100, yeah, again 1100, 1100, and so on. So 1100 is the repeating part, so we can write this as um, like this. So this is the equivalent binary representation of 250.8 decimal. So moving on, we can also represent or rather convert numbers from binary to hexadecimal. So this is a bit more straightforward than converting to decimal. So basically you follow this table here. So for decimal of 0, you have this binary equivalent. So basically each hexadecimal number has a binary representation which is a nibble. Okay, so if you have the binary digit represented as a nibble, then you can directly map the hexadecimal number like this. So the idea is, like, whatever the decimal number is from 0 to 15, since we have the base 16, we are concerned about 0 to 15, and then we have the hex equivalent numbers which starts from 0, but after 9 the remaining from 10 to 15 is denoted with these letters A, B, C, D, E, F. So we have a mapping ready here, and whenever we encounter a binary number, we can divide it into nibbles and then map those nibbles directly to the hex number. So for example, 1101 is divided into two nibbles, and then the direct mapping can be done from this table. So 1101 is your D and 1011 is 9. So this is D9 in hexadecimal. For fractional numbers also you can do the same. So the trick is to find a pattern of 4 within the binary digit. So let's say if you want to convert any other random binary number, let's say 10010. Okay, so this is a 5-bit number. Okay, So these are the 4 bits, and then you imagine there are 3 zeros in front. So then you can divide it into 2 nibbles, and then you can use this table. So 0001 is equivalent to hex of 1, and 0010 is 2. So this number is 12 or 12 in hexadecimal. Okay, so this way you can convert from binary to hexadecimal. So let's do this exercise, convert this particular number to hexadecimal. So the first integer part is fine, this is 1110, and from this table we can directly write this to be E. So this is E, and then the decimal comes, or the dot comes, and 011 can be thought of as 0110, and that corresponds to 6. So basically this is E6 in hexadecimal. We can perform different arithmetic operations in binary domain also. We can add two binary numbers, and basically we have to remember the basic rules. 0 plus 0 in binary is 0, 0 plus 1 or 1 plus 0 is 1, and then 1 plus 1 is 1 0. Okay, and then we can apply this. So 1 plus 1 is 1 0. You have the 0 here, and the 1 goes to carry here, and then you add this. This becomes again 0 with a carry 1 here, and then you propagate in this direction to get the entire sum. Similarly, you can do subtraction by the same logic. So in decimal subtraction, when you subtract a number, let's say 256, and then you subtract 186 from it, let's say, so you have 6 minus 6 0. But whenever you are subtracting 8 from this, so you imagine that this is actually 15 with a carry here, and then you have 7, 15 minus 8, and this carry comes here added to this number, so then it becomes 2 minus 2 is 0, so you have 70. Okay, similarly you do the same logic here. The only thing is that here, when you are subtracting, let's say a 1 from a 0, you imagine that this is a 1 0, and then that subtraction will give you 1, and then this number comes here as carry. Okay, and then you do 1 minus 1 0, and so on. So the same logic applies, but with changed rules. Okay, multiplication in binary, again we do the same thing as we do in decimal. We perform this operation by expanding the multiplier as a sum of 3 numbers. Okay, and multiplying the multiplicand by each of these in turn, and then adding the result. This is exactly what you do when you are multiplying two decimal numbers, right? So the same operation happens for division also. The same basic rule of division applies, but with some change of um, rules. Okay, that applies to binary. So if we are dividing this number by this number, so the first thing is that this number like can be contained 1 times. So you take the first 4 numbers, and 1011 can only go up to 1 times to fit this, and then you take the subtraction here, and then you have 0011 as the subtracted result, and then you keep borrowing 1 number from here. Okay, so when you borrow a number from here, this number comes here, you put a 0 here, then again you borrow another number, they put another 0 here, This is still not divisible by this number, so you essentially borrow another number, okay, and you get 1100, okay. So then this is 1 times this divisor, and then you do the subtraction, you have a 1 here, you borrow this 0 again, and then probably you cannot proceed further because you are done with all the digits, okay. So you have 10 as your remainder, and this is your quotient. So same logic of division that we apply for decimal numbers. So now we will briefly go through the concepts of digital logic. But in this course, in this microcontroller course, we take a somewhat higher level view compared to the gate level analysis that you did in digital electronics module. This means that we are here only concerned more with the behavior of the digital logic blocks, okay. Like what is the functional behavior, okay, like what they actually do, rather than concerning with the low level implementation of the blocks, like how they are made in terms of gates and logic blocks, okay. So for example, we know that a combinational logic block is always designed using the basic logic gates, like AND, OR, NAND, NOR, and NOT. And there is always a logic diagram showing how these gates are connected between each other to fully understand the block. But mainly, we all we require, uh, especially in this microcontroller module, is the behavior of the block. So I will explain this with an example. Let's consider the example of a half adder. So you know, a half adder takes two numbers and produces a sum and a carry, okay. And that is what you need to know when you are studying microcontroller, that it takes two numbers a and b, and there is a block in between, and the output is a sum and a carry, okay, rather than focusing on the gate level details. So for example, a half adder is built with an exclusive OR and an AND gate. So we are not concerned about this in this module, okay. All we are concerned is the function, okay, that it performs, which is the function of the inputs. So the sum is the function of the two inputs, and the carry is the function, another function of the two inputs. So that is what we are interested in. So the logic blocks are connected together using lines and buses. So line is just a single conductor that can carry a 1 or a 0. So when we have many lines together, we call it a bus, and we represent that in this way. Instead of drawing all the 8 lines, you can just draw a bold line with a stroke here saying the number of lines present in that bus. And then you can define a register which can be defined as some inputs and some buses, some input buses and some output buses. So you can see this probably explains what we meant by the fact that we are only concerned with the function or the behavior of a block. So we are not drawing all the individual gates inside this register. All we are concerned is the input and the output. So the input is a clock signal, then there is a load signal, and then there are n data lines that are input and n data lines that are output, okay. So the n can be any number. It can be an 8-bit register which is capable of storing 8 bits of data, and this requires an 8-bit data bus at the input and an 8-bit data bus at the output, as shown above. And then of course the registers are synchronous logic elements, so they need some clock signal to function. Then the arithmetic and the logical operations store at least one of their operands in a register. So when adding two binary numbers, one or both numbers may be read from the two separate registers and the result could be assigned to a third register. And this behavior, a common way to describe this behavior of a digital logic design is known as register transfer level. So this describes how the data is moved between registers. So this is again an example of another block, which is RAM or random access memory. So this requires a clock input again. So this is again a synchronous block. It also requires a read input and a write input, and then some address bus, which is consisting of M lines, and then some data inputs and some data outputs. And there are n input lines and n output lines, and we see that there are m address lines in this block. So this means there are 2 to the power m addressable locations, each storing an n bit word. So you have m address lines, so each of the m address line can have either 1 or 0, two combination. Okay, so therefore you have 2 to the power m possible combinations that are possible. So therefore in this RAM you have like these separate addresses. Let's say if this is a box, let's say imagine this is a box and this has uh, different compartments or different addresses, okay, like this. And these addresses can be starting from 0, 1, 2 up to 2 to the power m. Okay, since there are m address lines, and each of these address can contain an n bit word, because the data input bus is n bit and data output bus is also n bit. So here you can have, in each of these addresses you can have 0, 1, 2 up to n. Okay, so essentially you can have total 2 to the power m address locations, and each of them stores n bits. So you can have the total capacity of this RAM as 2 to the power m times n, these many bits. Okay, so this is the total capacity of this RAM. So when data is stored in, when data is to be stored in the RAM, the write line is set at a high and the read line is set at a low, because essentially we are writing data. And when the data is read from the RAM, you do the opposite, you set the read line to high and write line to low. So let's do an exercise. Let's say we have a RAM block which is required to have memory storage for 8016 bit words. So how many bits wide does the address line need to be, and how many bytes can be stored in this memory unit? So basically you have 8000 addresses. So as you saw, if you have a m bit in address bus, then you can have 2 to the power m addresses. Okay, so this 2 to the power m is your equivalent to 8000 according to this problem. So basically your m will be a number log of 8000 to the base 2. Okay, and since you cannot have a fractional number of lines, you take the ceiling function of this, okay, denoted by these two notations. So whatever be this number, you calculate and then you take the greatest integer nearest to that number. So for example, here we have this worked out. So this number log of 8000 to the base 2 gives you 12.97, and the greatest integer nearest to this number is 13. So therefore your address line should have at least 13 lines. Your address bus should have 13 lines, and 2 to the power 13 is 8192, so there would be 8192 addressable memory location. So you needed 8000, at least 8000, and you got 8192, so which is okay. And then if you have 8192 addresses, each of 16 bits, which is 2 bytes, then you basically have 8192 times 2 bytes, or in other words 16384 bytes that can be stored in this memory, or that is the capacity of this memory. So I leave this problem. So there is another similar problem as an exercise for you, and then I will stop here today. This is the end of this first lecture, and I will see you in the next video lecture. Thank you.